And so there are a couple of things here. I have kind of a collection of topics that we want to talk about. As we do this, my goodness, if you don't understand something, please tell me so we have the chance to clear it up, as there won't be more opportunities. The test is written and ready to go. And so, obviously I can't tell you what's on the test, but I can talk about some of the topics. The one thing that has come up is the difference between the addressing modes. So, not just the addressing modes, but the way you encode them. So if we have something like, say, LDA alpha, is that base or PC relative? Is it base or PC relative? How about neither one? Okay, well, what is base and PC relative then? Are they addressing modes? No. So what are they? Huh? What does that mean? PC relative, base relative? If they're not addressing modes, what are they? Yes?
It'd be a foundation for the offset?
It's a way to encode. Now understand, an addressing mode is how you get to the data. Where is it? So this is very specific. LDA alpha means go to this address, and starting at this address, take one word and put it in register A. That's what that instruction says to do. You can encode this two different ways. You could use PC relative or base relative. Are both possible? Yes, they are. Are both correct? Well, under the right circumstances, they could be. But PC and base relative, these are not addressing modes. These are not addressing modes. There are ways to encode this mode. Okay. So suppose I had LDA at alpha. Could you encode this with PC relative or base relative? Yeah. Okay. So obviously it's not an addressing mode. Well, what's the difference between PC and base relative? So they're both offsets. This is true. But let me picture, let's draw a picture. I like pictures. Suppose that we have a memory map here. So this is a memory map of your program. Now you have executable code up at the top here. And down here you've got labels which refer to memory locations. So this is a great big, this is all data. And this part is the executable. All right. So these are chunks of memory that have been allocated. Obviously, I want to make a distinction here. If this is alpha, then alpha means the starting address of that chunk. That alpha does not refer to a whole chunk of memory. And it's important to make that clear distinction. Sometimes students confuse variables and labels. So what is the value of alpha? Is alpha the contents of memory? Suppose we have this. 2, the word 2. Is alpha 2? No. It isn't, that's a mistake. All right. So to the task at hand here. Explaining the difference between these modes. Okay, so we're going to say this is alpha, and down here, let's say this is gamma. Okay, so as we go through memory, we start here and we move down. So we'll assume we're right here. So we sequentially march through memory, executing each instruction as we encounter them. All right. So the spot we're on right now, we're going to execute this instruction. Of course, we had to read it before we could execute it. So we've read this, but we haven't done it yet. The program counter is right here. You with me so far? The program counter is a register in the CPU. It's a register that holds the address of the next instruction to go. But at this point, this instruction here hasn't yet been executed, and the program counter points right after it. So what happens now? We execute the instruction, and then we'll fetch the next one and do the same. So we have this execution cycle that is fetch, decode, execute, store the result. Fetch, decode, execute, store the result. So this is the execution cycle for or forever do, fetch. The next instruction from memory, decode it. Execute the instruction. Store the result. If any. This is the execution cycle. Fetch, decode, execute, store. Once you fetch, you move down to the next thing. So this is maybe PC++ inside here. Then you decode it, you execute the instruction, you store the results of it, and you keep going. Okay, questions about this so far? Okay. The distance from this spot right here to this spot right here, do we know what it is? Can we figure it out? I mean, there's memory here. This has an address, and this has an address. So can we figure out the distance from one to the other?
Absolutely.
Yes, absolutely we can. We can do subtraction. And so if we use the address of this instruction, we add 3 to it, so we get to the program counter. That's the +3 part. So the offset is the destination minus the source +3. Are we good? You all understand this? Okay. So the distance from here to here is in bytes. So I can encode either one of the instructions. We want this one or alpha without the add. So I can encode these. And it's going to look like this. I'm going to have 6 digits. And here is the offset. This is the number of bytes from the program counter to alpha. Easily to calculate. Any questions on this? All right. Now the problem comes about if the distance is too far. So there's a compromise here. You can get to any address in memory if you know what it is. But if we make this bigger, then instructions are longer and it takes longer to execute and it slows the whole system down. So we want to keep those reasonably short. So for PC relative, the range of addresses backwards or forwards. You can go either direction. What's that? Oh. PC, relative. The range is minus 2048 to 2047. And in hex, this is 800 up to 7F, 3 hex digits. So you can go forward or you can go backwards. All right, so the general heuristic, if you're designing an actual assembler, you're not, but if you were, would be that the PC relative mode is always available, so you can try that first. And if it doesn't work, then try the base mode. And if that doesn't work, then throw an exception. So this is always available because the program counter is always available. It's a piece of hardware. Then the base mode. So first of all, it has to have been enabled. You must have a base directive in your program. So we might see something that looks like this. Base gamma. LDB gamma. So the restrictions, well, let me write the range first. This is a forward only, 0, 0, 0 up to F, F, F. Oops. This is 0 to 40, 90. They have to be forward, never backwards.
What?
Somebody asked him. Again, parallel, I guess. All right, so it must be enabled. It must be enabled. It must be a forward reference, never backwards. And of course, it's got to be in range. Yes, Ken.
Is there any point in using base before 2047?
Well, the whole purpose for this, the reason why you have this base mode, is very often you may have a large chunk of memory and it's too far away. And so using base makes it possible to avoid using format 4. So if we were to calculate, well, imagine that this is, let's say this is x 2000 in size. Well, it's obviously out of range because there's a certain number of bytes here and then there's 2000 in hex here. Well, in hex, you've got to 7FF, so this is obviously too much. So you could not access gamma. So this instruction, LDA gamma, would be impossible with PC relative mode. Now, does it matter where it would be in the executable block? No, it could be the very last instruction right here. And it still would be too far away, so you could not use PC relative mode. So the only choices then is to use either format 4 or use base relative. So if we say base gamma, rather than trying to calculate, okay, so we use base gamma, do something different. Eta, this, right here. Okay, so if we want to do LDA eta, then if the distance from here to here is too much, too many bytes, and there's 2,000 in hex right here, so obviously it's too much. Instead, you can use base mode, which means you can calculate from here to here. And that is a very small number, it will certainly fit. That's the point of base relative. Oftentimes, you may have fairly large chunks of data at the bottom of the program in the storage allocation area, and to get to the ones at the bottom, they're too far away for PC relative mode. Yes?
But you only want to do it when it's too far, not if it's within range, you don't want to ever do it.
Well, you can do it either way. So you have loaded into this base register the address of gamma. So you have two registers now in the CPU that have a fixed point from which you're measuring distances. The PC, the base register. So is it faster to do one than the other? No, they're both registers, they both work. Yes?
If this is the first pass, how did you know the address of gamma for the LDP commit?
You wouldn't.
So if you try to use base relative on the first pass?
Yeah, this won't work, right? This will not work. Does everybody understand why? Does everybody see his point? I mean, I didn't actually talk about doing this. You would absolutely have to do this. The reason is you can't do this instruction using base mode because you don't have it loaded yet. There's nothing in the base register. Since base isn't available yet, you haven't loaded it, you have to use PC relative or format 4. So this particular instruction, given these distances, you would have to use format 4. Yes?
So if we do LDA gamma and we use base mode, would that just be 0 for the address?
Yes? Yes. So when you calculate the displacement, which is what you would do, you know, your instructions in format 3 have this form. This is the opcode and flags. Opcode and flags, and then here is the offset or displacement. Same way to say the same thing. So when you first do this, if you can't use PC relative mode, you can't use base mode because it's not loaded yet. All right. So with base mode, it says go to the base register and add this offset to it to get here. With PC relative mode, go to this register, take that number and add the offset to get here or wherever it may be. Does everybody follow me? Do we understand? Okay. Now I have a question for you. This has a pound sign and this doesn't. Why not? Why is there no pound sign here, but there's a pound sign here?
Because the base reads from the register that has the address of
Well, this says load. What does this say to do? Load the address again into the base register. Okay. Why pound sign in front of one of them and not the other? I mean, wouldn't it be consistent? Yes?
Is it because it starts with gamma?
No.
Isn't the first one just saying that the base is gamma? But the second one is loading the address itself.
Well, what is gamma? I mean, it's important to understand this concept. What is gamma? Yes? So, all right, completely different. Let's talk about this before we go back to that. It's important to understand. Suppose I have, and let me use a different label. memory now, we have 3 bytes. It creates that chunk of memory, right? What is the value of foo? What is the value of foo? No, this is the point I want to make. What is the value of foo? The value of foo is 00106. The value of foo is not 10. This is a mistake. This is an error. This is the wrong way of looking at it. So understand that we have this data structure we call the symbol table or SymTab. And as you go through that process with pass 1, all of the labels in the source code file, you assign a value to all of these user-defined symbols. So your SymTab has the key or the label and then the value here. We have foo, and the value of foo is 00106. Foo means the address where this starts, and that's all it means. Does it mean 10? No. Not in any way does it mean 10. Now, we might have had also further up, maybe we have, making this up now, to C bar E Q U 10. What is the value of bar? It's 10. Why isn't it 2C? Because you manually set the value in the symbol table to 10. And so this is 10. That's the value of it. Typically, though, the value of a label is an address unless you've set it manually with EQU. Therefore, the value of foo is what it is in the symbol table, which is 106. The value of bar is what it is in the symbol table, which is manually set to 10. You with me? Okay. So back here, still pushing this. No one's come up with what I wanted to hear. No pound sign, pound sign. This code is correct. So why a pound sign on one and not another? Yes?
I need to do another one. What is base do?
What is what?
Base do.
I didn't hear you.
What does base do? The base command.
What does base do? Enables base mode.
Oh, okay.
Not an addressing mode, but that you can encode it using base relative as opposed to PC relative. So you have this base register, and the only purpose for this base register to exist is because it enables this mode. So if you set the base to gamma, that is, you take the address of gamma and put it in the base register, then you can calculate the distance from that address to here with base mode. It allows you to do an offset. The only other choice you would have would be to encode the full 20-bit address. And we want to avoid that. Yeah.
I guess my question I still have is if you're encoding base mode on the first pass through, how is gamma in the symbol lookup table already? Or how does it know that that's what the address is?
Oh, it wouldn't. It wouldn't.
So
So
you would
does
just
everybody
leave
understand
it
this
blank?
question? It's a good one. All right. Pass one goes through, and it goes down and it looks at each instruction. And the only goal for pass one is to assign an address to every line of code and to put all of the symbols in the symbol table. That's the only reason or the purpose of pass 1. So let's say we started at address 0. All right, base gamma. What's the next address? 0. Okay. Now, plus LDB # gamma. Okay, so now we need, did we do anything with # gamma? No, we did not. Why not? Because we don't know what gamma is, we're not there yet. So our goal here is to get the addresses of every line of code, and then we're going to put things in the symbol table. But we don't need to know the address of gamma to know that this is 4. So we're not doing anything with it. Then we keep going, and when we get to alpha, we know its address, so we put it in the symbol table. And then we get to data, and we know its address, we put it in the symbol table. We get to gamma, we know the address, we put it in the symbol table. Then on pass 2, we actually encode all of our instructions. So it is pass 2 where we get here, we have plus LDB # gamma. And we go look up gamma in the symbol table, and in fact, now we have it, it's there. Know what the address of gamma is. Does that help? Does that? Okay. Yes?
What was pass 2 again?
Pass 2 is where you actually encode the instructions. So essentially in pass 1, you ignore this operand field entirely. You look up your instruction. All right, it could be format 1. It could be format 2, like add R. It could be format 3/4. Okay, knowing that information, then when you read each opcode, you know how much space it takes. If there's a plus in front of it, it takes 4. If there's no plus, it takes 3. So you look this up, and it's a format 3/4 instruction. So if there's a plus, it's 4. If there's no plus, it's 3. So that's how you get the addresses. But you don't actually look at this, not yet. Yes. I'm worried about this test. I'm anxious to answer your questions. Kenny.
So pass 1 is strictly for the opcode, and pass 2.
It does 2 things. Pass 1. Put an address for every line of code. 2. Look up and store in the symbol table all of the labels you find. Well, if this label is here, gamma, then at some point it has to be in the label field over here. If it doesn't, it's an undefined symbol. So all of these guys have to be over here at some point, probably at the bottom. It's when you find them there, you look them up and store their addresses, and now they're defined. You're with me? But if I have add, I don't know, XYZ, does that mean then that there must be a label XYZ? The fact that this here in the operand field is XYZ, does that mean there has to be an XYZ label somewhere? And their answer is yes, there must be. You have to have defined XYZ, otherwise it has no meaning. So this can take 2 forms. Number 1, it can be a label, XYZ word 50, let's say. Or it could be XYZ EQU 10, something. But it must be, there must be that label somewhere. Otherwise you have an undefined symbol. So the first pass, you identify all the labels or user-defined symbols and put them in the symbol table. The second pass, what happens? you're gonna encode add XYZ. So you go look in your symbol table, and if there's no XYZ, you have an undefined symbol. You're with me? You follow me here? Okay. So I still don't have an answer to my question. If you have another one, shoot, I'll hold it. I'm not letting go of this yet.
So if there was just one letter, say if it was just X, that would be considered a numeric constant, taken as an address.
Say that again?
And here, like, one of the examples is you have C,
Uh-huh.
and you say it's a numeric constant taken as an address.
Yeah.
So is that something different?
So, okay, yeah, this is a whole different ballgame, a whole different question. So let me answer Kenny's question. Add $100. Okay, what does that say? So you wouldn't probably do this. This is most likely an error, but it's still valid, it's possible. This says, go to address 100 or 100. Take the word you find in memory at this location and add it to register A. It is exactly and precisely the same mode as add alpha. It's the same mode. Well, you probably wanted to use alpha or something like alpha. This, you do all the time. This, you don't do. To have a hard-coded address where you're going to read something from memory is most likely an error. We use these symbols like alpha so that we don't have to calculate the addresses. If you add some more code and move your data down, then when you reassemble, that's okay because alpha will then have a different address. If you're hard coding this, and that's why I grayed out the top of that addressing modes chart. They're legal, but probably a mistake. You know, in the bad old days, in the late 1940s and early 1950s, when you wrote code, you wrote in machine code and you didn't have these symbols. So you might have something like add, well, what did you find? We'll leave it. So then you go back and you have changed the code and added some new instructions. Well, this memory location has been moved down, so you're going to have to go back and change it and calculate where this data would be. So maybe you have 10C instead of 100. So we don't do this anymore. That's what assembly language is for. You give labels to things, and labels change if the code changes. The assembler in Task 1 figures out where everything is and assigns them addresses. So what is this? Well, that would correspond to a value over here of something you'd look up. Maybe you have something like gamma here, and it's got an address. So let's say the address is 00, 2000, 208B. I just made it up. All right. So if that is the address there, again, then can I say add gamma? And is that any different from add 0208B? Those do the same thing, precisely the same thing, right? So with this one, your assembler looks it up and inserts this address when it assembles the code. So those two instructions do exactly the same thing. This mode is grayed out in the top of that chart I gave you. It's still legal. You can still do it. Okay. somebody knows, why does one have a pound sign and not the other? Anybody? Yes.
Because it's the address of the label?
Well, isn't this the address too? Aren't you putting the address of gamma in the address register? You're going to use the address of gamma to enable the base. You are. Let's not belabor it any further. The pound sign is an addressing mode, but there's no addressing mode in play here. Yes?
Is the first one the contents from memory at
No,
gamma?
it's not. It's the address. It's the address. So let me, okay, so we haven't really seen this. We haven't seen this, but let's say delta. Delta. Yeah, right? Delta. Word. Yeah. Zeta. Word. Delta. Can you do that? Is that even legal?
Just making the function of the base.
No, it's not.
Taking the address.
Yes, it is. Remember, it's really important you remember. This goes in the symbol table. So suppose we have this value. I'm going to make something up again. That's the address, 01060. Okay. So over here you have delta. 01060. That's the value of delta. Okay, so what goes in memory? What goes in memory here? Well, it looks like this. So we have word 10, 00000A. Then zeta, we have yes.
If we put an @ sign in front of delta, would it work?
Here,
Yes.
this is my whole point. Nonsense. Why? There's no addressing mode in play here. There's no addressing mode. There's only delta and nothing else, and it means one thing. What is delta mean? What is the value of delta? It's address, and there's nothing else. That's all it means. Addressing modes, on the other hand, go with machine instructions. Therefore, LDB pound sign gamma makes sense. This is an addressing mode, the immediate value of gamma, which is its address. Here, there are no addressing modes. That's not a machine instruction. Therefore, doing something like this is nonsense. It doesn't mean anything. There's no machine instruction, therefore there's no addressing mode. You have a symbol and it has a value, and that's all you've got. So when you assemble this, does the CPU know what a delta is? No, the CPU has no clue. So when this is assembled, you get this. It makes sense to the CPU. But there's no addressing mode in play. Yes.
So if you said EQU delta 10, then that would work?
You could say delta EQU 10, and then it would be 10. Yes. Why? Because over here, instead of 01060, you'd have 10. Similarly, if I said zeta word bar which we have in our symbol table, you get that. In other words, if you have a label there instead of a number, then you have to go look it up and replace it with the number in the symbol table. In the operand field, if there's a label there, a user-defined symbol, operand field. Well, operator field, operand field. In the operand field, if there is a label, a symbol, then you go look it up and replace it with the number. That's what the assembler does, right? So if we have something like LDA foo, then it makes no difference whether I have LDA foo or I have LDA 00106. Is that the right number? Okay, those are the same thing. What the assembler does is it will take this and replace it with this. This is the value of foo. So then both instructions say go to address 00106 and read the word in memory found there and put it in the A register. Both of those do exactly the same thing. Similarly, LDA $ foo does exactly the same thing as LDA $. These two do exactly the same thing. The address of foo goes in the register. This address goes in the register. Does the same thing. So we have addressing modes. We do have here, we have LDA alpha. That's one. We have LDA $ alpha. That's two. We have LDA apt alpha. You with me? There's one more. LDA alpha X. Now you could replace alpha with its address and get exactly the same result. So all four of those are perfectly valid if you put the actual address instead of alpha. And those are the ones I grayed out at the top of that sheet with the legal addressing modes. They're constants. Questions? So how do each of these work? What does this mean? So let's clean up and let's do an example. All right, what's the address of beta? The address of beta. Yeah. A word is 3 bytes, 1 C plus 3 is 1 F. Everybody with me? Okay. Now, there's no pound sign alpha, but it's still the address of alpha because that's all alpha is. The address. Okay, so what is this actually creating in memory? And then we have the value of alpha. Okay. Now if I say LDA alpha, this is the easiest case. What's in register A? Register A has what in it? 6. This is an addressing mode. This says go to alpha, and starting at alpha, take one word and put it in memory. This is the standard memory reference. Now, if you look in the appendix of the book, it tells you how these work. Go to alpha, starting at alpha, take one word, and put it in register A. It's the 6. Yes, you with me? Okay. What about LD? So this A has LDA pound sign alpha. What is in register A? The address of alpha. Now sometimes we're writing 5 digits, sometimes 6. Words are 6 bytes, or 6 digits, I'm sorry. However, the format 4, the address is 5 digits. So the largest possible address is 20 bits. But words are 24, hence the difference. But it's always a 0 if you have a 6-bit or a 6-digit address. Okay. LDA pound sign beta. Same thing, right? Okay. LDA at beta. At beta. What's in register A? 6. So what does this say to do? LDA at beta. Go to beta and read the address in beta and go there. There's the 6. Do you see this? So this is a whole lot like the indirection we have seen with Java. Person P equal new person. So it's the same idea. P dot set name. Java. All right, we have P, and it's got an address in it. So over here on the heap, we actually have the person. Go to that address and do something. Go to that address and read the value you find there. It's the same idea. It's the same thing. You have a reference or an address instead of the value. Okay. Now I want to add one more here. What's the address of the next label? Let's do something different. Let's call it zeta. What's the address of zeta?
2.
Yes. Everybody see that? It's just arithmetic. Okay. All right, now then, that's 10 words. Now let's make an assumption here that we know what's in these. I'm just gonna say they're even digits, even numbers. 2, 4, 6, 8. 2, 4, 6, and so on. All right. Now let's also assume that the X register, X is a register, that it has okay, L, E, A, zeta, X. What's in the A register? Go to zeta, which is 00022. Add what's in the X register and go there. All right, this is 2, 2, 3, 4, 5. This is 00025. What's in the register A? 4. So these are your addressing modes. Yes. Okay, this is 2, 2, zeta. 00022, 23, 24, 25. This actually is easier than many of you want to make it. Yes?
Why is that a 4?
00004. I mean, I just made up the content so we could illustrate the addressing mode. Okay. All right. Questions from you guys?
I have one question.
Mm-hmm.
When you went to add beta, you went to 1C, but it says that it's 1F, the address.
No, beta is 1F. All right, so we went to 1F, which is here. C, D, E, F. We went to 1F. We took the word there and treated it like an address. Go to that address and dereference it. Well, that's 1C. Go there and take a word.
Okay.
So it's the indirection part of it. It's like a variable that has an address in it instead of a value. But we could do this. We could say int x equals 2. All right, we have an integer. It's x. It's got 2 in it, period. Now I can say int star y equals n x. Well, what's in y? What's in y? What's the address of x? Who knows what it is? We don't know, but it's an address. Y is a variable. It has a value. That value is an address. So if we dereference it, star y equals 4, does that change x? It does, yes. What does this say to do? Go to the address in y and set it to 4. Yes. So that's the addressing mode that we've been talking Yes.
They're gonna need to know like all the different opcodes and their functions.
Yes. In a sense. I mean, you're not going to write in this assembler. I'm not going to ask you to do something. You know, calculate the nth Fibonacci number using this assembly language, programming language. No, we haven't even really looked at it too much. We're more concerned with turning it into machine code and how it actually what runs. Well, that's secondary. However, you need to know the opcodes, the sizes, which is in the appendix, and that will be part of your test. The last 2 pages of your test will be the start of the appendix where it gives all of the opcodes, what they do, their sizes, and the formats. So I'm going to give you that. What concerns me, I'm going to ask you about the addressing modes. You need to know those. There's 4 of them. This isn't really hard. I hope you're on board with these. I'm going to ask you to hand translate to machine code. So you're going to do the look up the opcode, set the NIX, BPE flags, calculate the displacement. You're going to have to do that. I promised you it would be on the test, and in fact it is. So you will have to hand translate, hand assemble a small set of machine or assembly language statements into machine code or object code. So you're going to have this chart thing. And you're going to have to give me the address and the machine code. And then here are the instructions. So you'll have something like LDA food. So you're going to look up the opcode. Well, I think the opcode for LDA is 00, which makes it easy. Then you're going to do the flags. Well, is foo in range? If it is, for PC relative, use PC relative mode. But the first step is going to be to get the addresses of everything. That's the first thing you want to do. Go right down the line and get the address of everything. Then, if you know the address of foo, can you calculate the displacement? Sure. So practice this. Make sure you can do it. Other questions? Yes.
When we went over this sheet, you translated the LDB delta into 69100 BEO, or BE0 rather, and I didn't know exactly where the 6910 came from. I know the 0BE0 is the offset to get to delta.
Okay.
But I don't
Well,
know
that's,
what
okay, so that's a format 3 instruction, is it not? LDB, is that what it was?
LDB.
Okay.
This might be the one where we had to switch it to format 4 because we couldn't read.
So LDB. Let me see here. I've got some more stuff. I imagine that I have the,
It was the first instruction, so it's right under the base.
well, I don't know which handout you have. So do you know what the opcode for LDB is? I'm not sure I have that sheet. 6A? Okay. So the opcode is 6A. Well, we're home free. We have 6, 8, N, I, X, B, P, E. So what was the actual instruction? Pound sign delta. Okay, so do you have the address of delta? And the address of this instruction?
0BBF.
So the offset was okay, is that correct? That wasn't a problem? Is the first part?
Yeah, I think so.
All right. Is it N and I. Well, this is 0 and 1 because it is immediate. Is there an X bit? No. Is it base relative? Can't be. PC, yes. E, no. Therefore, we have 6, 9, 2, and then the 3-digit displacement.
Does anybody else have this? Because that's not what I
You
have.
have to change it. That was the one we had.
Is that the one we did because it was too far away and I had to make it a plus?
Yeah.
Okay, so it's a good thing I'm allowed to make mistakes. You guys aren't, right? If the displacement is too far and you change it to this, that changes the equation. Then this is true, but it's no longer PC relative. It's no such thing. It's this, which would be not 692, but 691, and then 5 more digits for the actual address. What would have to be in that case. Does that make sense? You with me? So I checked the exam, what I asked you in code carefully. There's nothing that's impossible there. So in this case, when I wrote it down, I made a mistake at that point. But it has to be PC relative. That's the only choice. And if it was out of range, then you have to use format 4 period. All right. I want to say something about groups. It's been a source of concern, aggravation, irritation to many of you. I know that if I ask you all to give me a confidential statement here, and I ask you the question, would you rather work on this all alone or part of a group? I bet 90% of you would say, let me do it by myself. I bet most of you would say that. Dealing with groups is something new and unfamiliar and uncomfortable for many of you. I get that. But that's part of the education here. That is, as part of your curriculum, we are required to give you group projects. You get them if you take software engineering, but that is an optional or an elective course. So there's no guarantee that you're going to end up taking that class and doing team projects. So the curriculum committee sees this as a good place to do team projects. So I always do team projects in this class. Sometimes the teams don't work out very well, and sometimes they do. But it's not okay to say, all right, I sent him a message, he didn't respond, so screw him, I'm not going to bother with it. It's not okay. You have to find a way to make this work. It's essential. And to come to me and say, well, we weren't able to get our project to turn it in because so-and-so didn't show up, or this guy, he's really busy and he doesn't have time. If you're a computer science major, then your computer science courses have to be your first priority. And if you're counting on this as an elective for your major in the engineering department, then this does need to be a priority. So my message is you have to find a way to work with your team members. I did disband a couple of teams that seemed non-functional. I'm not disbanding anymore. You know, I know this isn't your first choice, but it doesn't matter. You have to do it. You should be aware, too, that very often students come to me and say, well, would you mind giving me a reference? I've applied for a great job at pick a company, Teradata, Qualcomm, Sony, wherever it might be. And if I know the student and I'm comfortable doing so, I say, sure, I'll be happy to put me down. Well, one thing they ask me quite often, were there any team projects? Do you have any experience with this student working as part of a team? And sometimes the answer is yes, sometimes it's no. But they're particularly interested to know how you functioned as part of a team. Because guess what? When you go to work for Qualcomm, you're not going to work in a cubicle all by yourself and no one will bother you. you're going to be expected to work with a team. And if you can't do that, then your prospects aren't great. I know that this actually matters as much to the hiring people as your technical skills. What does that do to a company like, say, Teradata, if they have 5 people working on a team and there's one guy that nobody can stand? One guy that bitches and bellyaches and moans and never is done, and everybody has is substandard. I mean, how's this going to work out? You know, I know this guy that is absolutely brilliant. He does SAP. You guys know what SAP stuff is? It's a German database company. High-end, complex, difficult. SAP programmers make piles of money. Well, this guy is a crack expert at SAP. And every time I see him, he's got a new job. Either they fired him or he quit and walked off. He's difficult. But you don't want to be the one that's difficult. So find a way to work with your colleagues in this class on your teams. Number one, it will dictate, and in a large part, color what I have to say about you when people call and ask, and they do ask, they do. 2, it's part of your education. You're going to have to work with teams, and you're not going to like some of them. I know I've done this too. I did consulting work for a nonprofit a few years ago, and there's one guy on that team I would have, you know, if I had a gun, I would have shot him. I'm not as even-tempered as some of you guys are. He was horrible. Again, I understand. Here I'm volunteering my time. I got this guy to deal with. Anyway, it's important. It matters. It's part of the curriculum, part of your training. So find a way to make it work. Now I've offered this carrot here. There's no stick. That is to say, if you do all the work and your work is flawless and you get and your team gets an A on that, the whole team gets the A. However, there is a carrot. At the end of the day, when I review this is a fairly small class. I'm getting a real sense of who's doing what here. If you're going to end up with a B, but you did most of the work, guess what? You're not going to get a B. You're going to get an A instead. So there is a reward down the line here. You have to trust me. I think I'm a trustworthy person. That what I've told you I will do. If you have done more than your fair share, and your teammates have let you down, okay, they profited from your efforts. But at the end of the day, the projects are 50%, the tests are 50%. So let's just say you get a C on that test on Wednesday. Somebody's going to. I'm pretty sure. But if you did extra work on the program, then I can boost your grade at the end. And I will. So there's a payoff for you being the good citizen here. In industry, it doesn't work that way. In industry, you carry the team and they give you a pat on the back and say, attaboy. And maybe they give you a nice review, but they're not giving you half of that guy's salary, I assure you. So, you know, they're going to expect you to do that. Well, I'm going to give you a reward for doing it. So please, sometimes it's not fair. Also, please do your best not just to get the work done, but to get along. You know, sometimes we have groups where there's a tyrant. We're doing it this way, and this is how it's going to go. And if you don't like it, you're an idiot. And I'm going to tell Mr. Riggins you're not doing anything. I mean, you know, you get some guy that wants to just dominate and dictate everything. That's not good. But there are too many people that are just sloughing off, doing very little, and letting the rest of their team do all the work. And trust me, I know when people are doing this. Plus, I'm going to ask you on the final, in complete confidentiality, what percentage your team members contributed to the overall effort. I'm going to ask you to tell me, no one's going to see it but me. And if it bears out and matches what my own experience with you and my observations have been, then when Qualcomm says, we want to ask you for a reference on so-and-so, if you have done nothing this semester but profit off of other people's work, I'm going to have to tell them what I do sometimes, which is, you know what, between you and me and the fence posts, I'd pass on this candidate. It matters. And, you know, when you're going in and applying for a job, I'm going to do my best for you guys. I won't lie for you, but I want to do my best for you. But there's a few people that don't want to do their fair share, don't want to do the work, but want to profit from it. And, you know, it always comes around to bite you. Eventually it does. So please find a way to make friends with your team members and work things out. It's part of the reason why I let you form your own teams. Thinking, okay, like-minded people work well together. And some of the teams I have disbanded, that's true, but if you're one of the disbanded teams, you still owe me work. You still owe me work. It's 100 points, which is one letter grade in this class. So, some of you had a very easy ride so far this semester, and this, you know, has been a disappointment that you haven't done more. So I'll get off my soapbox now. Last semester I had more A's than any other grade. And I hope that's the case this semester. So please, knock it out of the park.